Hello everyone, I am Brunno Vargas, a member of the research group composed of Mr. Matheus Constantino and Dr. Fabio Kanizawa from the Thermoscience Laboratory at Universidade Federal Fluminense. This study presents the development of a test section for experimental determination of a local heat transfer coefficient during in-tube flow. This presentation is organized in the following order: introduction and motivation, objectives, concept development, experimental evaluation, conclusions, and next steps for future works. The heat transfer coefficient is defined by the Newton's Cooling law, dividing the heat flux by the difference between surface and fluid temperatures. This is a primary parameter for the design of heat exchangers. Therefore, the knowledge of innovative techniques is crucial to build more efficient industrial processes. A large number of predictive methods for heat transfer coefficient were classified by Moreira into the following groups. However, only the direct method and the Wilson method will be highlighted in this review. The direct method technique is applied when all variables of the Newton's cooling law can be independently measured, which is the case of the present experimental approach. As an example, Tibiriçá performed experiments for determination of heat transfer coefficient during convective boiling. The heat flux was imposed by adjustable electric current through thin-walled test section tubes by Joule effect. The inner surface temperature was estimated solving the heat diffusion equation and the outer surface temperature measured by thermocouples. The fluid temperature was estimated from an energy balance along the main flow. Then, the heat transfer coefficient could be calculated. Uncertainties of the order of 23% were reported for this method. On the other hand, Wilson proposed a graphical method that avoids the measurement of the wall temperature under condition of more than one convective heat transfer process. This figure represents a shell tube heat exchanger with internal flow at controlled operational conditions and condensing fluid in the shell side. The overall thermal resistance given by convection in shell and tube sides and heat conduction through the wall. By ensuring that the internal flow corresponds to the dominant thermal resistance, the heat conduction through the wall and external convection was considered constant, and the heat transfer coefficient in the tube side would be a power function of the fluid velocity. Observing this equation, it is noticed that 1 over Ct and Cc could be estimated by linear regression as reproduced in this graph. The mean heat transfer coefficient are calculated based on these parameters. Uncertainty of the order of 20% were reported. In the context of heat transfer with phase change, the heat transfer coefficient varies significantly in the length direction due to the flow pattern. Therefore, elaborating a methodology to obtain the local heat transfer coefficient is very convenient in these cases. Based on the previous discussion, this work provides an experimental approach for local heat transfer coefficient during in-tube flow with a heat flux sensor composed of a thermopile. Finally, validation of the method. This figure depicts the test section concept. It is composed of a thin-walled copper tube, which is coated with epoxy resin of uniform thickness. In steady-state condition, the one-directional heat flux is obtained from the conduction thermal resistance and the difference between the outer and inner surface temperatures of the epoxy layer, which is measured by a thermopile. The inner copper surface temperature is evaluated from the heat diffusion equation and the temperature T2, which is measured by a thermocouple fixed on the outer surface of the copper tube. The test section is composed of a copper tube of outer diameter of 6.4 mm with inner diameter of 4.8 mm and 200 mm long. The epoxy resin layer has 3 mm thick. The first figure represents the arrangement of thermocouples on the copper tube. The helical shape minimizes heat flow non-uniformity due to wires. In this figure, we can see how it looked during the construction of the test section, and here, how did it look after applying the epoxy resin. In this experimental validation, the main flow is heated by electrical resistor wrapped around the heat flux sensor in order to allow imposed controlled heat flux. In this circuit, water is pumped from the thermostatic path that controls its temperature. Adjusting a needle valve and observing a barometer, it was possible to control the volumetric flow. Then, the flow was directed to the test section where it was heated by electrical heater and finally returns to the thermostatic path. The complete circuit was thermally insulated by using elastomeric foam. In this experimental validation, only single-phase flow and steady-state conditions were evaluated. The first picture shows the electrical resistor wrapped around the test section, and here, after placing the insulation material around the test section. The determination of equivalent thermal resistance is crucial, because precise value of thermal conductivity of the epoxy resin is unknown. To do so, the epoxy layer thermal resistance is obtained dividing the temperature difference by the net heat transfer, where QM is the amount of heat transferred to ambient, evaluated by thermopile measurement of the elastomeric material, and this term is the thermal energy dissipated by the heater. Experiments for thermal resistance in the vertical axis were performed varying the heat flux from 2.2 to 3.2 kilowatts per meters squared, which is in the horizontal axis, for fixed flow rate and 3 different temperatures. According to this graph, the thermal resistance of the epoxy layer has a small variation around its average value of 2.73 degrees Celsius per watt, indicating that this approach is independent of the operational temperature and heat flux. Then, it is possible to estimate the heat flux dividing thermopile data by the thermal resistance of the epoxy layer and the area. As a validation procedure, tests with water at 20 degrees Celsius were performed to compare the heat flux obtained by the developed heat sensor to the reference value evaluated from the electric power and heat flux leaving the test section. According to this figure, it can be noted satisfactory agreement with deviation within 1.5%. Finally, the heat transfer coefficient is calculated dividing the heat flux by the difference between the surface temperature and fluid temperature, which is obtained by energy balance. This graph compares the heat transfer coefficient obtained by the present methodology, which is in the horizontal axis, with the corresponding value obtained by analytical method in the laminar regime with constant Nusselt of 4.36 and the Gnielinski model in the transitional turbulent regime. The electrical power was maintained fixed at 3.36 kilowatts per meter square during the experiments varying the volumetric flow. For low mass flow rates, the compatibility of values is more satisfactory than for higher flow rates as noted. A possible cause was the difficulty in guaranteeing the steady-state condition at higher flow rates. Thus, minimal variation in the thermopile measurement caused observable deviations in the heat transfer coefficient. The thermal resistance uncertainty is composed of dispersion of experimental data, which is given by the product between T and S, and another term that accounts for systematic error due to uncertainties of other parameters. Similarly, the heat transfer coefficient uncertainty was calculated by systematic error. This table presents the list of uncertainties for the main parameters used in this study. The heat transfer coefficient can be determined by this method with uncertainty up to 90.2%, which is lower than those reported in modified Wilson plot. In order to summarize, this study presented an experimental approach for determination of local heat transfer coefficient for flow inside channel with heat flux sensor based on thermopile. The thermal resistance of epoxy layer presented negligible deviation from its mean value, indicating its independence from operational temperature and heat flux. Uncertainties up to 6.2 and 9.2% were estimated for the heat flux sensor and heat transfer coefficient. It is expected for future works to construct a test section of other diameters, to validate for other operational conditions, to perform experiments with a heat exchanger configuration, and in phase change problems such as convective condensation and critical heat flux. Thank you for watching this presentation.